So the outline of my presentation is first of all I'm going to talk about something uh, very general. First, something about open clusters, then what is the problem about the star membership, uh, the data that we use in our research, and then I'm going through the model of proper motions and the clustering algorithm that we use to find stars in the open clusters. Then results and finally some conclusions and reference about the work. So first, open cluster, there are many definitions about what is an open cluster, and mainly depends on what are the topics that you want to study in this cluster of stars. So this is a brief definition of what is an open cluster that I like it, and it's more like a concentration of stars and that share some kinematic and stellar properties. So here we see a few open clusters extracted from the Theta Sky survey. And what is the census of the open cluster? So there are many works that have been performed on star membership, and many of these studies try to extend the list of membership in these clusters, even for open cluster and lower cluster. For example, the first that contains many targets are the Karchenko in 2013. Then with the new generation of data like Gaia DR3 or DR2 or whatever, many works have been performed on this topic. For example, Cantat Gaudi in 2019, Castro Guinal, again Cantat Gaudi, and the last one is Hunt, who update membership list for many open cluster and global clusters using Gaia DR3. Many of these works use different algorithms to uh, see what is the performance of the uh, algorithm to obtain stars. So the problem how to find star is that when we are looking for some specific points in the galaxy, this is a representation, a schematic representation. So we had some problems, and the question is how to find stars in a cluster given their information like astrometric, including coordinates, proper motions, and distance, and the photometric information. So the big general problem is that there are many stars in front of the cluster and behind the cluster, for example, here. So how to obtain this only these stars? It becomes in a specific and a classic problem, and there are many techniques to tackle this kind of problem. So the data that we use the Gaia data release 3 and for Pleiades Precipion Blanco 1. And why we use this open cluster is because the main reason is because they are very close to the sun. And the other characteristic is that their proper motions are large enough compared uh, to the field. So we can see in the vector point diagram that the stars in that clusters tend to get away from the background. So this is very helpful for the proper motions model. We will see this in a while. So the proper motions model is very simple. Only use proper motions in as ascension and declination, and use two probability density functions circular for the clusters, and elliptical for the background. So we can combine these two probability density functions to find the joint probability and use the Bayes theorem to compute or estimate the membership probability for a star to belong for the cluster and for the field. This is on the basis of the proper motion of the star. Depends on the proper motions for each one. So we compute this membership probability and use this to define a threshold, and we decide what is this threshold. In our case is 0.5, and all of stars with a membership probability greater than 0.5 can be considered as part of the cluster. Then the clustering algorithms, there are many clustering algorithms, many density based like DBSCAN and optics, which this algorithms tries to find high densities of data. Many distribution based like the Gaussian mixture model that assumes that data is from a Gaussian model, for example. Central base like K-means, and many others like the hierarchical base like HDBSCAN and BERGE, the balanced iterative reducing clustering hierarchies. So we use DBSCAN, and how this algorithm is helpful for finding cluster of stars. So the algorithm is very simple. It depends mainly on two hyperparameters, mean points and epsilon, which mean points is the number of points inside an epsilon region in the data set, to consider a point in three classes. First, core points, border points, and outliers. So here it's a schematic representation with mean points equal 3, taken from Cantat-Gaudin. And you can see here that the 3 green points are considered core points because for each point we define an epsilon region, and we see that in this region at least there are 3 points. So if the points satisfy this condition, is considered a core point. In the case of border points like the blue one, it doesn't have at least 3 points, but it contains core points, so it is considered the border, like the last part of the cluster. And the last one, the outlier, which they are considered outliers because it doesn't include many points. So results for the Pleiades Percipian Blanco 1. First of all, for the star membership with the proper motion, we use, in order to estimate the parameter of the proper motion model, we use maximum likelihood estimation using the likelihood function, and to estimate uncertainties on the parameter, we use McCormick Monte Carlo, validated by the German and Robin statistics. This table shows the results for the Pleiades Percipian Blanco 1 for the 3 clusters, and here we have the parameter for the proper motion models with their uncertainties and the Gell-Mann and Robin statistic. This is the corner plot of the posterior probability function, because with Markov we can sample the posterior using likelihood. In our case, the likelihood is the joint probability density function given the proper motions, and for this we use an for prior that ensures the range for each parameter to be computed. And for each cluster we can observe that the algorithm gets very accuracy to sample these parameters. Then the DISCAN algorithm, we use the algorithm in a 5-dimensional astrometric space with coordinates, proper motion, and parallax. And we follow a similar procedure described by Castro-Guinard. First, we compute the nearest neighbor distance, histogram of the data, and store the median value. Then, for each dimension, we sample from the Gaussian kernel and data with the same size of the data, the original data, for an average of 30 repetitions, and store the epsilon random because it's a random sample using, in this case, we use the Metropolis hosted. And the final epsilon was determined as the average of the 30 repetitions and the k nearest neighbor distance of the original data. Here is the history of how this sample of nearest neighbor distance have been performed. In red, we see the region of Pleiades, the entire data set. The blue, the simulated data for one repetition. I say that this was done for 30 repetitions. The orange, the Pleiades from the proper motion model. And we see that all of these share a similar peak of the distribution. So that's why we use the average and not the minimum in the case of Castro-Guinard. We see here the star magnitude results, and the first and big and general result is that both algorithms finds almost the same number of stars in each cluster, and the final sample was using the cross-matching of these two results. Then we estimate distance, age, metallicity using the baseline software, and we implement the key model to find the radial density profiles, to fit the radial density profiles in order to find the core radius and the tidal radius. Here we have the radial density profiles using the best fit key model, and the dashed vertical lines are represent the radial, the core radius and the tidal radius. Finally, with the sample of the two algorithms and the cross-matching, we build the spatial distribution and plot the tidal radius in order to observe how these stars are distributed along the region of the cluster. So we see that in case of the Pleiades, they are more concentrated inside the tidal radius. The Praesepe have few stars at the outskirts of the clusters beyond the tidal radius, and the Blanco one, which is a cluster at high latitude, have a particular behavior because it tends to have an elongated shape. It is, of course, that many works shows that this can be produced because of the some apparent transformation of the coordinates because of the high latitude, but it can be considered also as tidal tails. But we have to go deeply to analyze this kind of particular results, because many tidal tails with cluster at high latitudes can be misunderstood as tidal tails that only is part of the transformation of the coordinates. And this is the color magnitude diagram for the three clusters, Pleiades, Praecipia, and Blanco 1. And the red line, the solid red line, shows the best isochron computed using the metallicity and age shown in the diagram. And we see here that for the case of the Pleiades, there are stars in this part that try to go go away from the isochron, maybe because it has been reported in the literature that they can be considered as fast rotators, but we have to go deeply in this in order to explore this kind of behavior in these stars. And conclusions, the star membership was performed in the cluster using DRF3. And the proper motion model is useful for clusters with high mean proper motion, because for clusters with low proper motions, both the density distributions uh, can be part of the background. I mean, the both distributions cannot identify what is the circular distribution. So it's like the circular distribution is inside of the elliptical one. And that's why the main reason that we choose to perform this this study on these clusters. Both algorithms find similar number of stars in each cluster. And of course, the key model describes very well clusters with spherical shapes. We find and estimate the stellar and kinematic properties. They are very similar to previously values reported. And the last one, distortion, the spatial distribution of highlighted cluster, for example, Blanco 1, can be misinterpreted as tidal tails. This can be studied very carefully, because we can misunderstood many elongated structures in clusters that cannot be uh, tidal tails. These are the reference, and thank you.